Linear Algebra student, this video is for chapter 4.4, coordinate systems. So we have been talking about basis, or actually this is basis for a vector space. For vector space or a spanning sets. The reason why we do that is we want to impose a coordinate systems on vector space V. What is a coordinate system? So you should be aware of coordinate system like the x-axis, y-axis, like that. Like if it's a 3D or if it's x and y, the y-axis and x-axis. And because of that, we have bases of 1, 0 and 0, 1, right? So 0, 1, which is E2, right? And here, if we have three coordinate like x1, x2, x3, normally this is this is x2. Normally this is x1 or x, or y, z, x3. Then we also have 1, 0, 0, 0, 1, 0, and 0, 0, 1 as the standard basis. So why do we need other bases? We actually had spent a lot of time in 4.3 to discover if a set of vectors are bases for R3 or a spanning sets. So what happened is we want to use new base to rename our vectors. So just like in standard base E1, E2, if I have a vector 1, 6, which is here. So this is the coordinate, this is the origin 0, 0, 1, 6 is here. So this is a vector 1, 6, this is 1 and then 6. I can actually impose another base, B1, B2. B2 is kind of longer, but it's landing, and B1 is almost the same as E1. So you can see X and B2 actually is like on top of each other vertically. But once I plot this new coordinate system, X become like -2 away from the origin, and then just one above 0, right? So this new vector, this new coordinate for X now become -2, 3, or -2, 3. So you can see the same vector, in this case in the 2D space, actually can be represented in different coordinate based on different bases. So the bases are how you orient the new coordinate system. So this is one reason why we want to introduce new bases. Why do we need new bases? Because a lot of times like movement or the way we describe the vector or points are more convenient when they're in different bases. So first, Theorem 7. Theorem 7 is called the unique representation theorem. That tells us that if I have a base B1 to Bn for vector space V, then for each x, there is a unique set of scalar C1 to Cn such that C1 times B1 all the way to Cn times Bn would equal to x. That means I won't have, because if it is a basis, then there should just be one set of new coordinate. Just like physically, if I have a R2 environment, I can only label x one way. There is not another way I can label x in the new basis. So this is a unique representation theorem. And let's introduce some new term. So we already know that B equal to B1, B2, Bn are the basis. We usually use the capital B for the basis. Then this new coordinate that used to represent x, and having these weights of C1, B1 up to Cn, Bn will be represented as x with a bracket, and then a small b, which represent the basis here, and as a vector of C1 to Cn. Right? So this is the coordinate of x, but in reference to the base b. And likewise, x itself, usually we just write x or x based on the standard matrix. So x based on the standard matrix is usually written in this way. It's not C. It should be X, kind of like E like that. So that means elementary matrix, elementary standard basis. We usually call it x1 to xn, just like earlier when we call 1,6 for x. That is the x. We don't write the basis because it's standard. And then the way we write it would be, how can we find this x uh, um, now, because because x is defined by that. So if you write it in a matrix form, that means x would equal to a matrix B1 to Bn, just like a matrix equation, right? And then you have a vector C1 to Cn as the weights, just like when we solve a system of equation like that, right? So this is a matrix times a columns vector, and this column vector would be the coordinate. We call it the vector coordinate based on B. B1, B2, B to Bn uh, is called a change of coordinate matrix from B to the standard basis. It's rather long. It's called the change of coordinate matrix. What do you change it from? From B back to X. So using this, if you multiply by the new C1, Cn, that would give us what the real standard matrix is. Okay, so just know this name. This is called the um, um, this is called the coordinate vector coordinate based on B, xb. Oh no, this is xb. This is the real matrix, real vector. This is x based on B. And the relationship between them would be the OX is equal to the change of matrix formula, which is just all the B together times X of B. So with all this definition now, we're going to solve some question. So of course, the first things is find the coordinate of x in the new basis. How do I know what the new coordinate would be if I know my new basis? So it would actually, so just look at this. It would be this matrix A times the new C1, C2, which is the new x1 to xn based on B, equal to the standard matrix, right? This is the definition of the new basis. So to find x1 to xb, we are to solve this equation. Now there's two ways to solve it, right? Two ways to solve it. So this is the unknown. This is the unknown. So this is actually solving the systems of equations, so we can use augmented matrix of B1 to Bn, and then the last one would be x1 to xn in the standard matrix. So if you solve this, it'll become RREF to solve, right? Just like in chapter 1. You should have, because it's unique, you should have 1, 0, 0 all the way x1 of B all the way to xn based on B, right? All these. And it should be 1. So you can use REF to solve it is really quickly, but because this is a matrix multiplication question, you can also find XB directly by doing the change of base matrix inverse times X itself. So this is an alternative method, either by multiplication or by solving using the augmented matrix and RREF. So let's do some example. First is there is a basis that they tell you that it is a basis. It's 1, 0, 1, 2. It should be a basis because they're independent and it's 2 by 2, so it should span R2. And it has a coordinate x of b equal to negative 2, 3. What is the vector x? So let's write down what is PB. PB is the new basis, line up together, right? You can switch between them because the coordinate actually refer to, if they say refer to -2, that means the first multiply this by -2 and multiply the second one by 3. So PB is this, and then the equation is PB times what? XB, which is -2, 3, is equal to x1, x2 in the standard base. So all we do is just do a matrix multiplication, which is 1, 0, 1, 2 times -2, 3. So do matrix multiplication. 1 times -1 plus 3, that is 1. 0 times -2 plus 6, plus 2 times 3, 6. So what is the matrix X in the standard matrix? It is 1, 6. So it is 1, 6. So we say vector X is actually the 1, 6 matrix in the standard matrix form, but in the B form, in this basis, it is -2, 3. Okay. I think this is describing what the pictures is about. So example 2, we have another basis, 2, 1, -1, 1. It is a basis for R2. And x is equal to 4, 5. What is xb? So we'll write out the P of B, which is a lineup of all those vectors in column. And then write the equation P of B times xb, which is what we don't know. And it's supposed to be equal to 4, 5, right? So now, so we will just solve this equation by, I can solve it by two methods. I can solve it by the augmented matrix method or inverse method. So let me do both of them. Do the augmented matrix method. That means this would be a 2, 1, -1, 1. The other side is 4, 5, right? So do augmented matrix RREF of this 2, 1, -1, 4, 5. I think I have, where is it? This one? Yeah, 2, 1, -1, 1, 4, 5. I do RLEF of A, and it's 1, 0, 3, 0, 1, 2. It is always unique though. Okay, so that is equal to 1, 0, 3, 0, 1, 2. Read it up. That means x1 equal to 3, x2 based on B is equal to 3, 2. I can also use the inverse method. That means find the inverse of PB. That means XB is equal to PB inverse times 4, 5 in the at the back. So PB inverse is, let's just do the new matrix. 2, 1, -1, 1. And then just say G to power inverse. Oh, it is kind of difficult. Then why don't we do the 4, 5? Just use these to do everything. Maybe H. Okay, new matrix H, and then I'll delete one column is 4, 5, right? So then I will do G to power negative inverse times H. Nope, times H. It'll be 3, 2. So I do the inverse of PB and then times 4, 5 is equal to 3, 2 in the formula. So they're the same. Okay. So you can use this method, which takes longer step, especially in the matrix, decimal matrix calculator. REF seems to be faster, so I usually do that. So, so this is how you can find the two coordinate. If you know the coordinate of the standard from the standard base, you can find the coordinate for the new base. If you know the new base coordinate, you can find the basis for the standard.